All right, welcome to Physics Club today. My name is Max Fever. I'm a Mossman Fellow here in the department. I've worked with Professor Lyman Page for the last 8 years on the Simons Observatory, and it's my privilege to introduce him today. Lyman received his bachelor's from Bowdoin College, his PhD and postdoc from MIT, and is now the James S. McDonald Distinguished University Professor of Physics at Princeton, where he serves as the chair from 2011 to 2017. He has won the Marcel Grossman Award, the Breakthrough Prize in Physics, the Gruber Prize, the Shaw Prize, and he is an APS Fellow and a member of the National Academy of Sciences. Lyman is an expert in CMB cosmology and has led ground-based, balloon-board, and satellite-based CMB experiments. He was a co-eye of the WMAP satellite, the founding director of the Atacama Cosmology Telescope, and is a founding member of the Simons Observatory. Lyman now also works on axion detection, and if you're interested in the axion searches at Princeton, come to Professor Saptarshi Chaudhuri's NPA seminar tomorrow. However, that's not what we're going to talk about today. Today, I'm thrilled to hear Professor Page's perspective on how far the field has come and where we're headed with the Simons Observatory. Please join me in welcoming Professor Page.
Thank you, Max. You're too kind. I'm going to focus mostly on the second part of that. It's great to be back at Yale. I don't think I've been here since the pandemic, so it's nice to be back. And what I'd like to do is I want to spend sort of the first half of this just talking about a general picture for those of you who aren't cosmologists, just about how we think about the universe. And then I'll get into a little more about one of the things we can do with the cosmic microwave background. So first, what is the cosmic microwave background and how we think about it? So here is a map of it. And this is actually from the WMAP satellite. And the next all-sky map after this was from the Planck satellite. And at this scale and this resolution, it'd be almost indistinguishable. And what this is a map of is it's a heat map of the early universe. And what I want to try to put together for you, and I should say this is the whole sky, this is a mole-wide projection. The galaxy, I'll show you what it looks like. If you look up in the night sky, so again, this is a full sky. The galaxy has been removed. That would be a stripe right across the middle. And a dipole has been removed, right? Our motion with respect to the cosmic reference frame has been removed. And then this is what's left. And from the picture we'll build is that we think of this as an image of some quantum field from the birth of the universe, now blown up across the sky and manifests as temperature variations and radiation. So when we look at that, we say, okay, what are the properties of that quantum field as expressed through gravity and through radiation? And to give you a scale of this is from the bluest blue here to the reddest red is about 600 microkelvin. Okay, so those are sort of the temperature differences measured. And by the way, as I'm going along, just please feel free to just yell out a question, right? This is so we can make sure that we're all on the same page. Okay, so this is from the birth of the universe. Actually, this picture, though the fluctuations come from then, this picture we'll see is from about 400,000 years after the Big Bang. And that's what so that's when we look out, we see this. This is, if you will, the edge of the observable universe. And now we look, and again, I'll build this picture. This is now what we see around us. So this is from the Sloan Digital Sky Survey. And these are galaxies. Okay, these are all galaxies, a couple of them. And for the most part, they're moving away from us, as long as you get a little ways away from us to get rid of local motions. But the picture is, right, early on, right here, right now, or not right here, right then, was the cosmic microwave background. And it's been replaced by this, right, from cosmic growth. So this is what's here now, of course, because this is measured from a telescope down in New Mexico. But we started out with that picture with these tiny variations. I should have said that the fluctuations there, that 600 microkelvin is about a part in 10 to the 4, 10 to the 5 of the 3 degrees of the absolute background, which was subtracted. So how did we get from there to here? And how do we think about it? And so I'll fill that out. And the picture is, right, if you had on your watch, if you could have possibly ever been around just after the Big Bang, on your watch, over a period of 13 billion, 13.8 billion years, you would have been immersed in that radiation to seeing these galaxies just right here, right now. Okay, so let's see about how that comes together. And I should also say, as we zoom through, this is great. These are all, I also want to say, I'm going to really focus on measurements, and I'll tell you where the interpretation comes in. The interpretation is that first picture is a quantum field from the early universe. That's getting pretty solid. The rest of this is this is all data. Those are all real galaxies. These are all just observations, right? Which is the key thing. For numbers, each one of those galaxies is about roughly 100 billion stars. Okay, and a good way to remember that is, I'll use Bill Gates is worth about $100 billion. Elon Musk, who's been in the news an awful lot recently, is about 3 times that. Okay, so he has $1 or a few dollars for every star in one of those galaxies. Okay, so that's a good round number. Another way to think about that number, because it's so large, it is the number of neurons in your brain. So sort of a nice number. And to put it together, or if you have a sweet tooth, a 6 by 6 meter cube filled with M&Ms is just 1 billion M&Ms. So you can sort of picture the amount of this number of stars in the galaxy. Okay, it's starting again. There we go. Okay, so that was nearby. Let's look further out. So this is from the Hubble Space Telescope. This is their ultra deep field. And you can see where it was pointing. There's a little picture of it with the Earth pointing out there near Fornax. And they have this image. And again, these are the ones with crosses are stars, right? So, but these are galaxies. And again, they're rushing away from us. And this image is about 1/50th the size of the full moon. So you can just go and count the number of galaxies in that image and then multiply, up to the full moon and keep multiplying. And of course, you use fancy algorithms to do that. And for some reasonable mass cutoff, you get about 100 billion galaxies in the observable universe. Okay, so you have to get what it means. What is the observable universe? We'll get to that in a minute. So there are about 100 billion stars in a galaxy and about 100 billion galaxies in the observable universe. Okay? Good. So, Elon Musk has however you want to count it, he's got a lot of money. Or else there are a lot of galaxies in the universe. And soon we're going to get this with JWST. Okay, so how do we think about that these all seem to be rushing away from us? So here's a picture. So this is Hubble Lamont found that the universe is expanding. And specifically that the further away an object is from us, the faster it is moving. So it just looks like this top picture. And in particular, in proportion to its distance, the velocity is increasing. And you'll see those are all blue dots, right? So you might think we're at the center of the universe. And I think I told you this before, but my father went to Yale. And so I grew up thinking that Yale was the center of the universe. But it's not that special, okay? So all observers see the same thing. Okay, so and you can just do this by adding the vectors, right? If you went to a neighbor and looked, the neighbor would see the same picture as us. Just add the vectors, right? And you see the same picture no matter where you are. And immediately that begs the question, well, how does this go on forever? How can this work? If I tell you there are 100 billion galaxies in the observable universe, how can this possibly work? Right? Because it's just you think it goes on forever. But this picture works, and we'll see how it does in a minute. And a way to think about this is definitely not as galaxies, and we can think of galaxies as the marker, definitely not galaxies exploding into a pre-existing space. It is rather, the way to think about it is that space itself is expanding. And that's a fraught phrase because it sort of makes you think that space, that there's a force that exists, that doesn't exist. That's not it. But it really acts like space is expanding. Okay, so that is, so you can think of it as, I'll even go more out on a limb, like almost you're creating space between galaxies. Okay, and you can take it away and you can create it, right? And that's the way to a way to think about it. And so it's easy to get things moving faster, faster than the speed of light doing that, because all you're doing is, if you will, creating space locally. Okay, and if you do this, you can also very simply, if you saw this picture, you just roll it back in time, right? You can get an approximate age of the universe, because it's just when these guys are all on top of each other, when space was much, much, much more compact. So let's ignore the expansion for a minute and see what that means. So by measurement, to say, as far as we can tell, the universe is infinite. And by that, this isn't a philosophical statement, right? By that, I mean there is no measurement that we have yet been able to make that can distinguish between a finite universe in space and an infinite universe. Okay. Instead, and here's how we think about it, is if you could freeze, if you could just stop the expansion and go anywhere instantaneously right now, everywhere in the universe would look roughly like that first movie I showed you, the second slide, the Sloan Digital Sky Survey. It's homogeneous. Every place is the same, okay, roughly. And we're in this Hubble patch. And again, roughly, to within factors of a couple, the size of that Hubble patch, that observable universe, is set by 2 times the speed of light times the age of the universe. And that's it. And so you can now imagine, if this is our Hubble patches, that's as far as we can have access to, you can just count up the number of galaxies in that. Okay, so that's why we can say there are 100 billion, roughly, galaxies in the observable universe. Okay. And now, because the speed of light is finite, right, because the speed of light is finite, these telescopes are like time machines, right? So as we look out, so here's the Hubble Space Telescope. As we look out, deeper and deeper, we look back in time. And it's just, that's it. So now you hear about James Webb Space Telescope. It's looking back to see the first stars and the proto-galaxies before all those galaxies that we now observe are seen. If you look back far enough, you see the microwave background out there as a sphere around us. We used to make these beach balls, and you can really think of it as it's like you're inside a beach ball looking at that big surface. You're looking out at the CMB. And all of cosmic history has played out from there to now. And we just see it rolled out. And as we get more powerful telescopes and better ways to measure the sky, we just probe this picture more and more. But most of what I'm going to talk about today is from that surface right around there. So this is why we think the CMB is the edge of the observable universe. And again, that's the size of our Hubble patch. So this is all without taking into account the expansion. And now we just add the expansion. And in this picture, what all the expansion does is it redshifts the light. So light from out there was emitted when the universe was much more compact. It's now expanded, and we see it redshifted. So the physics that gave rise to the microwave background, which we'll get to in a minute, happened when the universe was roughly in one dimension, 1,100 times more compact, so about 1,100 times hotter, right? Just by the, because it's about 3 Kelvin today, so it was a few thousand Kelvin back then. So that's sort of that's the conceptual picture we have, right? So if you were suddenly transported to the edge of the observable universe, and you look back towards us, where we are now, what would you see? Of course, you would just see the microwave background, right? Every place in the universe sees the same thing. Okay, so that's the framework. Okay, so now let's go through the standard model of cosmology in a few slides. So there was some. So the idea is there's some process in the early universe, and the most popular model is called inflation. And there's a question mark there because I think for many people, it's still not resolved whether that is the definitive model, but it's certainly the most popular and had the most research done on it. But the idea here is some quantum fluctuations existed early on in the Big Bang. The universe went through some huge process of the expansion of space, if you will, the creating of space, some huge expansion, took those quantum fluctuations and blew them up to be cosmic scales. And then the plasma, all the stuff that was in the universe, right, so those quantum fluctuations were then manifest as variations in the strengths of gravity. All the matter in the universe then fell into that, and clumped up. And that's what gave, I'll show you a little more about this, gave rise to the microwave background. Then the universe, so there's all the matter was clumped up, still plasma is clumping. And then the universe expanded and cooled, and got cold enough so that atoms could form. And when that happened, the universe went from being a plasma to being neutral. So here's the picture. It expands and cools, and then roughly half the temperature of the sun. So the physics of this is well known, right? This has been tested in the laboratory type physics. When it's about half the sun, you could form hydrogen. And now when you can form hydrogen, right, you stop scattering photons and then the universe is neutral. You stop scattering the photons. And so the CMB just free streams to us, more or less. There's some interacts with some things along the way, but that's second order, right? So that's why we really say that is a picture of the early universe from the age of decoupling. From this happened about 400,000 years after the Big Bang. So we say the light has decoupled from the atoms, and it's free streamed to us since then. So it free streams to us. Then stars start to form. And when stars form, they put out all this radiation, and that then reionizes the universe. And we can measure all of this. And so it reionizes the universe, and stars form. And then the whole process of structure formation happens from then. Now it's just matter starts to fall into these gravitational potential wells set down by some early process here, and forms all the structure around us now. So that was the first slide right there. That's the second slide right there. And that's the picture we have. And this is the expansion of space, very fast, slowing down normally. And then we'll get to in a little while, this is the cosmological constant taking over, which is again leading to this accelerated expansion. So that's the model. And we can pull it all together in this. This is this is like a classic, right? I'm sure there's some TV channel where they show classic movies. This is like a classic movie for cosmologists, right? So this is from the Sloan Digital Sky Survey, even from maybe before Nikhil was working on it. And this is back when the sky was not as full, and there's a little, unlike that movie, there's a little artist license taken with the galaxies, but these are the real positions of the galaxies. And this is just zooming out from us. So this is sort of a 3D version of that first picture. And we just scan out, and you can see things as they were younger. Those are what's called the luminous red galaxies that turned on when the universe was something like twice as compact as it is now. And then you go out a little further and you see quasars and the like, these sensors of active galaxies from when the universe was still more compact. And then you go out, you can see here all the way to the cosmic microwave background. So that's the picture, the 3D picture around us, and the process of structure formation just plays out from there to us. Okay. Oops. So let me just tell you a little about this. So this is the map of the sky with the galaxy in it, still with the monopole removed, with the 3 Kelvin average temperature subtracted. And let's just zoom in on a certain part of it, that little bit right there. We can zoom in more, and you can see all the way, right here, that here's 5 degrees. There's a characteristic size in that first picture I showed. That characteristic size is much larger than the resolution of the instrument, right? It's not like the red blobs. These are just, again, the temperature fluctuations. It's not like the red blobs are that big, or the blue blobs are that big. They're a certain scale, right? They're a size. So we can then go and just, there are lots of algorithms that have been developed over the years to do this, but an especially simple one, which is to me so illuminating, is you just go and you just stack. You just take the hot spots and you just make a little cutout around them and you stack all the hot spots on each other, right? So here's a picture. This is from the Planck satellite. This is just a cutout right around the North Pole. So next, it's a beautiful, clear, cold night tonight. You can go out, look up at the North Pole, North Star's right there, and there is a hot spot to the microwave background right around there, right? Just hold up your hand around there. That's about the size of the North Pole. That's what the CMB looks like right there. And for scale here, that's the full moon. And you guys are all from Yale, so you know, right? The full moon is never that close to the North Pole. Okay, but that's for scale. So the full moon's about half a degree, right? So that's what the sky looks like up there, if you could look at it in microwave eyes. So nothing magic here. Just go and get your microwave telescope out and look up there. Okay, so stack all those hot spots on each other, and you come up with this, again from the Planck telescope. And now that is, and those are the same scale, so you can see how it goes. So that is then a standard yardstick. And so how do we get the hot and cold spots? So this is, and so here's a way to think about it. So all of a sudden, now we've looked out to the edge of the universe. We have this, we've seen these hot spots. There's some characteristic size, and roughly, half degree, something like that. So how do we get this? And here's the picture, right? So remember, this physics is not, it's straightforward. So there's some gravitational landscape here, and it's not big, right? It's a part in 10 to the 5, so it's not huge, but so this gravitational landscape, the plasma is flowing into it, and in roughly the age of the universe at decoupling, so at 380,000 years, in that time, it's had chance to flow into a well of this size, right? Once, it's just fallen in, right? And that, since there's a landscape of fluctuations, right? There are a couple that are picked out because that decoupling happens like this. We're taking a snapshot of a response to plasma flowing into a landscape of fluctuations. And that's about 1 degree. So the spot size is just roughly the speed the plasma can travel and times the age of the universe at decoupling. And it's that if you just that's obviously a little crude. It's more subtle than that. But if you just speed of a plasma, I'm sure if you guys, studying for, you're taking stat mech or something, right? In a plasma, it's just c over root 3. If the plasma dominated by photons is the speed of an acoustic oscillation. So it's just c over root 3 times 380,000 years. And that's the physical size in meter of the hot spot or a cold spot. You could stack on cold spots as well. So now we have this fundamental mode, okay? And it's a footprint. Here are our hot spots, our average hot spot. And so we know the physical size in meters. And now this is numbers from the Planck satellite. Can just measure these things incredibly accurately. This is one of the most accurate measurements, I think, in cosmology. It's just a straight geometric measurement. So now we have the angle, we have the size, so we can determine the distance, the size of the observable universe. And then we know the speed of light. And so we can just compute the age of the universe. There are a couple of subtleties in here, but the first order or 0th order, this is the picture. And so we get that the universe is 13.8 billion years, plus or minus a percent. And that's it. And it's much, there's much, that picture is much richer than I showed you. Here is, now here's that first peak at about a degree, a couple times the full moon. So that was where most of the fluctuations are. That's the average hotspot size. But if you look more closely here, there are harmonics to that correspond to different, capturing the plasma oscillations at different phases. As you say, this is on the x-axis is multipole. This is just, for spherical harmonics, that's the same multipole. And this is the compression, and this is, sorry, degrees on the top, compressional peak. And then this axis is just the variance of the fluctuations. So this is just a power spectrum of the sky if you made it flat. And why we believe we have the right models, and you'll see more of this, is those are two different ways of doing the error bars here. But that black, those are the data with error bars. And the black line is the model. And so if you don't have a model that fits to this, it's out. And we've been able, the field, when I say we, have been able to exclude lots and lots of models with increasing precision. And to show you where that is now, or let me just show you the models, and I'll show you sort of the status of it. So the models, there's just six parameters. That's all you need to explain all those data and a whole bunch more that I'll show you. Here are 3 of them, the cold dark matter, and that's about that's where maybe those are the axions, right? And what actually I could just tell you this because let me just go back one. The cold dark matter, you can figure out which parameter goes to which parts of this curve and things like that. The height of that third peak relative to the first peak gives you the amount of cold dark matter, right? So this is the most precise measurement of the amount of cold dark matter in the universe. It's from the microwave background. Okay, so you can that's the cold dark matter. We have no idea what it is. Well, we know what it isn't. We don't know what it is. This cosmological constant, which has come to dominate the mass energy density now, was irrelevant in the early universe. And of course, the stuff of which we're made of, which are atoms. And that's roughly, those are 3 of the parameters. So that's the, those aspects of the model. And this is our universe, is what we live in. So here's the abbreviated then standard, and we can talk about the other 3 if you want later. So here's the abbreviated standard model. So sometime there was some quantum field impressed on the universe, a gravitational landscape, and we measure the characteristics of this field. I mean, that's how we think about this. Matter fell into the valleys to form all the structure that we know about, but only 1/6 of that matter is familiar to us. We don't know what the dark matter is. And now the dynamics of the universe, they're not driven by matter. The matter is becoming, in terms of dynamic factor in the evolution of the universe, is becoming irrelevant. It's all driven by this cosmological constant term. And why do we believe it works? So here's the current status of measurements. So that curve, I don't even plot WMAP anymore, right? That curve I've been showing you right there is the top one. And you can see how precise the measurements have gotten. And the RMS fluctuation of the anisotropy is about 110 microkelvin. And to give you an idea of the state, those two gray lines are the difference in the two most cited cosmological models, right? That's the difference. It's tiny. And you can go from there, from that, and you can predict this spectrum and now measure it with this accuracy. So this is EE, stands for the polarization. I'll get to that in a minute. And you can predict that spectrum, and we're starting to measure that accurately. And you can predict the cross correlation between those two spectra, and that's this right there, right? All with one model. It's huge amounts of data, and it's why we believe it. And that's six parameters, right, over this huge range. Okay, so are there other elements to the model? And there are a ton, right? I mean, what is the dark matter? You can say, what is the mass of the neutrino? There are just so many, how does structure form? There are just tons and tons and tons of things you can do with a microwave background. So, I mean, the first thing you should say, okay, cool, but you definitely support your CMB group, right? Because they're just it's so rich in what you can do. So one of the questions we're all after is, are there measurable gravitational waves from the birth of the universe? So let me go back to this picture, same picture as before. And if there are these gravitational waves, and I'll get to this terminology in a minute, the B modes, they should be manifest at large angular scales. And we'll get to what this means, R and things like that in a minute. But to give you a sense, so all those figures I've been showing you, images, are of this. So about 100 microkelvin variations RMS. These are about 90 nanokelvin RMS variations. So this is what we're looking for right now in the search for primordial gravitational waves. So how do we think about it? So gravitational waves, right, they're characterized by a strain. And so as the gravitational wave propagates there, it squeezes space this way, expands this way, squeezes that, does that as it propagates, hopefully indicated by these arrows. So we characterize it by a strain. And as now well known, so LIGO discovered these directly, I should say, from these two inspiraling black holes, right? And the strain they measured was 10 to the minus 21. Okay, just an absolutely stunning instrument. And that strain corresponds to the width of a human hair between us and Alpha Centauri. Okay, so tiny, tiny, tiny strain. And the frequency of them was about 100 hertz. So we're searching for these gravitational waves from the birth of the universe, from these just huge, roiling, massive fluctuations. And the strains could be as large as 10 to the minus 5. Okay, so huge by LIGO standards. Right, so this is roughly the size of a human hair. You have to be a little on the tall side here, but the size of a human hair over the height of over the length of our body. Right, so these are huge strains that we're after. But the oscillation, and really, it's better to think of them as standing waves. They're not propagating waves. Let's think of them as standing waves coming out of the Big Bang. They're about 100 cycles per age of the universe. That's sort of our frequency range, roughly. I think of them like if there's you can think of them like dimples on a golf ball, right? In terms of perturbations, right? Dimples on a golf ball. But it also means if you look at the quadrupole, right, the lowest one, it would be like the universe has overall been squeezed this way and expanded this way, or flattened, at about a part in 10 to the 5. Okay, so as I mentioned before, you saw that plot. I mentioned that the CMB was polarized. So I want to take a minute here because it's just such a fun thing. It's just cool physics. So how do you do that? How do you get the CMB polarized? So imagine So here's a little, this is from Matt Hedman's picture. Imagine you're an electron here, because electrons are our ultimate detectors for these gravitational waves. So if you're an electron sitting here, and now you're in a radiation field that has a quadrupole pattern. So in this picture, unpolarized quadrupole pattern. So it's the ceiling's cold and the ground is cold, and that wall's hot and that wall's hot. Okay. So now you're here, electron sitting here, but it's hotter, so its amplitude is higher. So it's going to drive you more this way than this way, right? So when you look at this electron here, you're going to see it polarized in that direction, okay? And that is because these electrons then are sitting there roughly during decoupling, and I'll show you in a minute why it has to be a special time. They're sitting there at decoupling, and they're little detectors measuring the local quadrupole of radiation. And why you can see it has a special time, so that's one polarization, but you can see the opposite polarization is oscillating the electron that way, is isotropizing the radiation. It's taking that cold radiation and scattering, that hot radiation, pardon me, and scattering it into the cold region. So this scattering wants to reduce the quadrupole. It scatters, so it reduces the quadrupole. So it takes a special time in the universe, and that special time is from decoupling. So it's a short amount of time through decoupling when you see this, and it's the electrons there sensing the local quadrupole. And the local quadrupole can be produced by a number of things, but it can be, among them, it can be produced by primordial gravitational waves in the CMB. Right? So those are the sensors, and that's the physics of what's driving it. So here's a simulation of what it looks like. And so this is 18 degrees. The background is the microwave background, just there. Again, that large RMS. Now, 100 microkelvin across the sky is huge to us, right? And these lines show the polarization. And that's so if we just looked up with polarized eyes, you could measure the polarization at all these points. This is a simulation, by the way. This isn't data, but the data are actually getting to look like this, okay? So you look at this pattern of polarization, and now you want to quantify it. And if you just look at it in a mirror, right, you can take this, if you look at it in the mirror and then compare. So the even parity modes are ones that stay the same, and the odd parity modes, the ones that flip, are called the beam modes. And let me just dig into that a little more here. So, this is Helmholtz made his theorem for dividing things into divergenceless and curlless fields for vectors. And these aren't vectors, right? These are little like toothpicks. These are two-headed vectors. They're spin 2 quantities, but a lot of it translates over. But you could still divide that image of scattering of toothpicks, if you will, into 2 types of polarization. One, E modes, which do not change under parity transformation, so they look the same in the mirror, and B modes, which do change under parity transformation, which shift if you look in the mirror, right? That becomes that. Okay, so you can draw the pattern, hold it up in a mirror, and compare. Just take the map, and you can see what changes and what doesn't. That becomes. Those are E modes, and those are B modes. So the polarization from the standard model, the one that you saw labeled EE in that earlier figure, is about 6.4 microkelvin RMS in E modes. And again, we're measuring this with I think the latest I've seen is a signal to noise of well in excess of 100. And the best limit on the primordial gravitational waves is RMS of less than about 60 nanokelvin from the BICEP experiment, or 57, excuse me. So good. So how do we quantify these beams? How do we quantify the amount of gravitational radiation there is? And it's just a ratio of the fluctuation power in the tensor modes, the gravitational waves, versus the fluctuation power in the scalar mode. So this is the gravitational wave component. That's the stuff on the far left, versus the usual anisotropy. And I should say here, it was probably on the last slide, that gravitational waves, they produce equal amounts of E and B modes. It's just that the E modes are swamped by that 6.4 microkelvin, right? When you're down looking at nanokelvin, tens of nanokelvin. So here's just, this is how it's quantified. So original inflation, when I was a graduate student, that ratio should have been 0.3. Okay, the current limit is BICEP has the record, is it's less than 0.04, corresponding to about 57 nanokelvin at 2 sigma. So all those early models don't work, like none of them. Okay, but there's a lot of creativity. So should be the R of 10 to the, there's a lot of models that seem to be coming in at R of 10 to the minus 3. And more than one. There's a whole class that looked like that, and that might be the magic territory for them. And so we're all trying to build experiments to reach that level. An interesting alternative, if the universe isn't inflationary, if it's cyclic, for example, R should be immeasurably small. So if we see some perturbations, some tensor waves, some B modes at this level, we will be able to say that the universe, it was not cyclic. And it's just because of the energy scales that are involved in cyclic models versus the inflationary type models. But if we don't see R of that level, we can't say that inflation is ruled out or anything like that, right? Because it can you just get different models. So that's where we are. And the primary challenges aren't going to be detector sensitivity, because we've just made incredible advances over the years. It's going to be in foregrounds and systematics, figuring out, peering deeper and deeper into the sky around the shroud of dust in the galaxy, and then just systematic effects. So that's sort of where we are. So here is a group of us working on this, and I'll show you a number of aspects. So this is the Simons Observatory collaboration, and there's Yale right there, and there are many people here. And I was telling someone earlier, every day I have above my computer screen a monitor of what's going on in the Simons Observatory from these guys right here. And so I think of you all the time. So anyway, so here's the group. We're building this, and this is a big, this is of course funded by Simons, as you might imagine. Here's the core suite of instruments. There's a 6-meter telescope here, which is just I don't know if it's 5 ACT or SPT telescopes rolled into one, something like that. And then here are 3 what we call small aperture telescopes. And what these are made to look at the search for these B modes. And because these are large angular scales, they were over on the left-hand side of that plot. We only need, and these are all diffraction limited optics. We only need meter scale apertures. So that's the observatory. That's a picture. It's all built. Those are all built. Taking data. Here's one of the small aperture telescopes. There are 3 of these. 2 of them are taking data now. And here is the group who deployed it to Chile. And this guy is one of you, right? So that's Sam Day Weiss, who was an undergraduate here before he came to graduate school, I think working with Laura, among others. And I want to show you the instrument here. So here is and to show you how sophisticated things have gotten. So this is about 1 meter across. And here are all the cold optics. It's like just a straight telescope, right? Here are all the cold optics. All that's at about 1 Kelvin. The focal plane's there, and this is all up at the site at 17,000 feet, taking data right now. And that's about 60 millikelvin. There are about 10,000 TES detectors there, all working at their expected noise level, mostly just dominated by the photon noise from the surrounding, from coming in here. And what's one of the things we're doing, and I'll just give you a sense of the type of measurements, is right here, there's a spinning half-wave plate. So it's in order, right, we're looking for this incredibly faint signal over large angular scales, right? And here we are, we have to look through the atmosphere, and it emits radiation. And so we have to be able to get down to there, and we have to be able to look at that side of the sky and then look 20 degrees away over there and say that those are different by, on average, we're hoping to get down to 10 nanokelvin, right? That's not an easy, if you tried to do it from Yale, it'd be tough, right? The sky's a mess, right? Doesn't matter. If you did it from Princeton, the sky would be a mess too, right? You need to get away from the atmosphere, right? You need to get to, so we're up, that's why we're up at 17,000 feet to get away from water vapor. So the sky becomes even clearer. And so I'll show you what this half-wave plate does in a minute here. But the other thing to notice, this is a 35-degree field of view on diameter. We are looking at tons of sky at a time, right? That's 35. So we're looking at these large swaths of sky and scanning this instrument around and spinning this half-wave plate and taking data. And I'll show you roughly why we have a spinning half-wave plate. And I should say this was built by our colleagues in Japan, and it's just a very cool device. It's levitated on superconducting bearings and has a specialized motor, and we read it out to fractions of a degree, and it's working amazingly. So here's and this is from another one of your guys. This is from a recent paper by Thomas Morris and colleagues. So this is what we have to look through. So this is a section this is just 40 minutes of raw data at 90 gigahertz, one of our primary frequencies. And it's moving, you can see it fluctuates a lot. And that's about 0.3 Kelvin right there, right? And we're trying to measure tens of nanokelvin. So, but you can see, right, it's a lot of low frequency data, noise in there. And if you look at the power spectrum, and here it is, those bottom two lines are 90 gigahertz corresponding to that. If you look at the power spectrum, not only can you figure out what it is really a straight Kolmogorov spectrum, right? This is just classic turbulence. It fits super well. So we understand it, but then what we do is we modulate, the half-wave plate modulates our signal up here to near 10 hertz, above the 1/f of the atmosphere. And so we are immune to all those fluctuations. And then we can go on from there. So let me tell you a little bit about the future of what's going on before winding up. Here is, this is again, this was recently funded to almost double the original number of detectors in here. So that's going to be happening over the next 5 years. The UK is building 2 small aperture telescopes, additional small aperture telescopes to go here. And then the Japanese are also building another small aperture telescope to probe. These are all going to be looking at slightly different frequencies. And the whole enterprise is called Advanced SO. But it's going to be coming online, this really powerful new observatory to figure out the microwave background and to probe it to these new depths. And as I said before, this is just one of the new things that we're going to be doing. So let me stop there, and thank you.
Any questions for the people on the mic?
I'll yeah. Talk loud. I can hear you.
90 gigahertz wave plate, but that's that big.
Yeah, it's sapphire, which is birefringent, and not only this actually measured in 2 frequencies. So this works from about 70 to 160 gigahertz. And so if you take 3 pieces of sapphire and cock them by the right angles, you can build up the bandwidth. But then sapphire in the millimeter has a huge index of refraction. It's 3.5, something like that. And so you reflect all the radiation off, if you did an anti-reflection coat it. And so we've tried a few different things. The one what we have, this is from Jeff McMahon's group in Chicago, is a big piece of alumina with lots of grooves on it. And their grooves are specially shaped so that they can be an anti-reflection coating over that bandwidth. And then that whole thing, so there are three, and yeah, so then you put it all together and you cool it down and you spin it up.
How much does it weigh?
It weighs, let's see, it's roughly
120 pounds or something.
So yeah, I was gonna say, is it that? The LF one, I think this is a little less. I mean, I can lift it, so I'm not, so. Yeah, so, we lift it carefully, yeah. So not, yeah, it's manageable. Yeah, it's a really impressive, it's an impressive device. And I can say, the tolerances are tiny. And so it's, if we're off, we worry about it going through the superconducting transition and all that stuff, and it sags a little bit. So we have to be pretty careful with it.
It's not bothered by the pulse.
No, that I think we have under control. So so actually all the sats do different things. We servo ours at 40 Kelvin, and we have enough heat capacity in this thing so that the variations up there are small. And it's 40 Kelvin. So yeah, I'd say that's for these instruments, that's the new magic sauce, is that guy, plus these 10,000 detectors, these transition edge detectors, which measure, these are come out of NIST and then Suzanne Stagg's group, is it measures two orthogonal polarizations at two frequencies, right? So these are really kind of neat devices. Laura worked on them as a postdoc. So. Yeah.
You talked about advanced SO. Do you want to say a little bit about the future beyond that and CMBS4 and?
Yeah, I think, so this is a very politically charged question. So and I can say this is not as, I'm not part of CMBS4, so I'm somewhat removed. I think, the South Pole site has been fantastic, right? All the BICEP results are down there. Our sister telescope, the South Pole telescope, is down there. And we sort of, with the Atacama Cosmology Telescope, have been, whatever, they make great paper, and then we think we have a better paper than they, that sort of thing. So that's been going on for years. So the question is, where are you going to make this next move to not 6, but say 20 small aperture telescopes, and not 1, but 2 large aperture telescopes to really push to the ultimate limits? And the South Pole's a great site, but there are infrastructure challenges, so a lot of people are looking at Chile. I'd say for the small aperture telescopes, I think people are waiting to see that we can demonstrate that you can make a measurement from Chile at the level of, say, BICEP or, within a factor of a couple. That hasn't been done. So that's got to happen. And I think when that happens, then, it's a good time to think more about the future. In terms of things like the neutrino mass, getting the sum of the neutrinos, it's no question you want to do it from Chile because it's all sky coverage. And that's just all about going deep on the sky. And plus, there's the overlap with the LSST. It's the overlap with with all these satellite surveys. You just want area. And from that, this picture, there's so many, this is pictures in the queue, well, right? So we have the CMB here, and we can now, so that's the surface. And we're now measuring the lensing of the CMB we're at 40 some odd sigma now, and we'll be better. And that means we're doing the tomography of the universe. We're measuring, so if you think about it as a shell, right, the CMB, we're measuring all the stuff inside. And by cross-correlating with these surveys, we're just picking out shells. And like at a redshift of 2, we can just tell where all the dark matter is. It's there. It's a clump, no clump, clump. You just pick it out. And that as these surveys get better and better, we'll do the tomography, just do that by redshift. And it's really stunning. So I think for that kind of science, Chile is in the future. For the other stuff, it's a wait and see. But I view it as the science is just so great, right? It will happen, and it's just a trajectory, and we'll learn as we go and improve, and hopefully all the funding agencies do the right thing at the right time to take advantage of it.
Have you ever heard of the cosmic axion background? And if so, what are your thoughts on it? And how do you think we could measure it, look at it, etc.?
Yeah, so well, you probably know more than I do about this, right? But this is, of course, going on here, right? So here, that dark matter could be axions, right? Which is really, I think this is what I did. This is really exciting, I think, to me, right? For years, it's been, was the WIMP paradigm, right? That dark matter, that 25% of the overall cosmic density might be WIMPs, which was great. But the experiments have gotten really good, and they're pushing the limits, and there's more to go. It's not, by no means is it done, but it's certainly, that's one lamppost. And there are other lampposts down around. I think axions are wonderful. And as you know, I should say, in the day with a bunch of people in this room, we work on axions because it's just so exciting. And it could be the dark matter and could, solve the CP problem. So it seems like it makes complete sense to me to look for it and look for it hard and look for it in lots of different ways. And there are lots of other dark matter candidates. One of the cool things about the CMB is you can, especially like CMB combined with all these galaxy surveys, is you can posit a dark matter particle. But unless it's, like fuzzy dark matter might be a little difficult because of the scales, but other things have identifiable effects, and you can look for them in the CMB because we're so sensitive to the dark matter, right? And so a lot of candidates are being constrained by the CMB, or starting to be, and that will just get better and better and better. And then the WIMPs, of course, will get better, and then we just think it's right around the corner for the axions. But we'll see. But yeah, I think that's an incredibly exciting direction, actually.
So you really stuck to the sort of observations here, which I appreciated.
Yeah.
In terms of what would convince you that inflation was the right theory versus or convince you that it was the wrong theory? Because the CMB is measuring some imprints of things. What else would you need to see to get you that?
I'll tell you, if R came out to be 0.001, that would kind of be it. And we knew it wasn't magnetic fields, right? It had the right spectrum. If R is that level, the floodgates will open in terms of the number of people going after it, right? If it's at that level, it won't be long before we get the index of fluctuations and all those things, and then I would be a believer. I'm sure other people would be too. I think everyone would be, not me. It's just, but obviously needs to be convincing. You need to see it in a couple of experiments. You need to see the spectrum of it and frequency and in space, right? You need all of those. And I should say, of course, the physics is so great, right? The Lightbird experiment, let out of JAXA, is also in the works. So that might be another satellite that just focuses on the large angular scales. So that's also that's also happening. So I think it might take some time, but we will certainly get to that level of 10 to the minus 3 on R. It's just have to be careful, that's all.
All right, let's thank Lyman one more time.
Thank you.